Lesson 1.5, we're going to look at approximating a line through data. And sometimes data lines up pretty nice. Like here I have a study about the number of chirps per minute observed in crickets versus the temperature of the environment the crickets were in degrees Fahrenheit. Or, for example, the average parts per million of CO2 in our atmosphere versus the year. Some other examples are blood alcohol content versus cans of beer. So a study was done with college students, and they were randomly assigned into groups, and they picked some women and some men and some people who drink a lot and some people who don't, and big people and small people. And they just had them drink a certain number of beers, and then the police measured their BAC. And you can see that, on average, the more beers somebody drank, the higher their blood alcohol content was a half an hour later. I found some other data on metropolitan regions, like big cities, and the unemployment rate in the city versus the murders per million in that city. And it seems there's a relationship that the higher the unemployment rate in a given region, the more murders there are in that region. And sometimes we try to approximate that with a line and talk about the slope, so how things are changing together. So let's just play around with that idea with some examples. So I'm going to go back and stick to the simpler ones. Oops, excuse me. And we'll look at chirps per million, and we'll look at CO2. I like working with this data in a spreadsheet, so I'll do a little with spreadsheet and a little on paper. So let's take a look at the cricket chirps here. Oops, there we go. So I have the data over here. Let's blow that up a touch. And I had the computer graph it to see that, yeah, things line up pretty good. And I had the computer guess at a line in there. And I'm going to use the second point and the last point because they seem to hit pretty good on that line. And I think that line kind of follows this trend of dots pretty well. So again, second point and the last point. I want to move this out of the way. And I want the second point and the, oops, try that again. Touchpads are sometimes annoying, aren't they? All right, I want those two. Let's highlight them. So what I want to do is find the slope and see if I can come up with an equation. So the rise would be the distance from here to here, and the run would be the distance from there to there. So let's copy that into my worksheet, my paper. All right, so here's my table. And these numbers aren't too bad. We could pencil that out. So let's see, what do we got? When we take a look at our slope, right? Slope is a rate of change. Rate meaning a division usually, and change meaning a subtraction. And here we've got a bit of both. Rate of change for us, we have an independent variable I'm calling chirps, and the dependent variable temperature. So my perspective here is that if I can count the number of chirps, I can estimate the temperature. And I find counting easier than estimating temperature. I don't know about you. Could go the other way, though. We could switch these two, and temperature could be the independent variable. And based on the temperature, we could predict how many chirps per minute we're going to hear from crickets. So anyway, so sometimes you can change your perspective on that. Sometimes there's only one way to look at it. Here, I think it can go either way. So we have change on our output. That's the numerator. And change on our input is the denominator. And I've decided that my output is the temperature, so that means I need to figure out what is 83 minus 59.5, and I need 195 minus 97. All right, so calculator might be handy to do that. Let's see, I think this right here would be 23.5. I did that right, and this one down here is going to be 90. Say that right? have that right. And that I can't do in my head, so I guess we're going to go back to the spreadsheet. So on the spreadsheet, I want to know what's the rise and the run. So let's see, I'm going to put that up here, rise and run. And my rise is this number minus that one. And I did pretty good there. And the run is this number minus that one. And I did pretty good there. So the slope for those two is just going to be the ratio of the rise over slash the run. So I get a slope of about 0.239. And these numbers here have 2 or 3 digits. So if I'm going to go for significant figures, I guess I have 2 digits that are significant there. So I should round that to 2 decimal places. And let's blow that up a little more. And that is a hair too big. There we go. So I think the slope is about 0.24 rounded. So let's add that. So instead of equal, we'll make that a wavy equals to indicate we rounded, and that's about 0.24. And just to keep in mind what those numbers mean, the top number is degrees Fahrenheit. Let's make a note of that. And the bottom number is chirps. So the division would be 0.24 degrees Fahrenheit per chirp. So interpreting the slope here, for every additional chirp I hear, I expect the temperature to go up about 0.24 degrees. So let's write that down, our interpretation for an increase of 1 chirp per minute. The temperature should rise by about 0.24 degrees Fahrenheit. All right, so that's what the slope means. Now, ultimately, I want more than just an interpretation. I want to get a line through those points to the best of my ability. So next thing I need is a starting point. Now, a starting point means 0 chirps. What's the temperature? That probably isn't going to be realistic if there's no chirps. It's kind of outside the range of our data, but that's how you find an equation. So I am going to get, let's see, a new page. I'm running out of room here. So let's copy this over to a new page. And we are looking for something like y equals mx plus b, where the variables are x and y. So x, again, is my chirps per minute. And y is the temperature in degrees Fahrenheit. And so far, I believe that y is equal to about 0.24 times x plus b. And so next thing I want to do is find that value for b. So to isolate this value for b here, I could plug in an x and a y that I know. So I'm going to go with that first point that I picked right there. And so all I do is plug that in for y and x. So if the temperature is 59.5, that means the number of chirps must have been 97. And now I can figure out what b is. So I have to multiply the 0.24 by 97 and then subtract it over. So a little calculator help for that. Show desktop. So let's see. I'm just going to use this as a calculator, kind of like scratch paper. I need to take that, what was it, 97 times the 0.24, and that gives me 23.28. And so then I'll subtract this over to the other side to figure out what b is. And then we'll test it out. so subtracting that from each side. So let's see, 28 from 50 is going to leave me 22. And 23 from 59 is 36. So it looks like 36.22 is my B. So I think an equation that models this situation right there, let's put it in green, would be y equals 0.24x plus 36.22. And if I go with the whole significant figures thing, then I would probably just get rid of the 0.22 and just call it 36. So how do I know if I did that right? Well, we can check in a couple of different ways. If I leave the 0.22 in there, or not, I could just plug in the 195 and see if I get 83 back. So I would wonder what is y if I plug in 195. And hopefully I get about 83. So I'm just going to add that to my spreadsheet, and I'm going to check a bunch of these numbers just for fun. Show. So let us insert a new column to get some room. And then I'm going to put linear equation. And my linear equation says that I should take that 0.24 times whatever the number of chirps is, right? That was my x, and add on to that the 36.22. So if my arithmetic on that was all right, I should get approximately the number I have here. And in some places it should match pretty good. All right, so 59.5, nailed it. 63 versus 61-ish, 67 versus, or 68 versus 67, 72 versus 72, 79 versus 80. Yeah, they're pretty darn close. Not too bad. So I found a linear equation that roughly fits this over here. So if we zoom out, see that picture. So again, and sometimes I'll do this on paper, but plot the points, estimate a line through there, and then pick 2 points that you think the line goes through and use those 2 points to find the line. And the kind of best general procedure for doing that is to first find the slope. So we did that right away, got that 0.24 by taking the rise over the run, and then plugging in one of the points, and I plugged in this point right here along with the slope, and that allowed me to find B, y-intercept. So let's try this again on a different example. And next page and new page. So let's look at CO2 over time. So these are estimates of the parts per million of carbon dioxide in our atmosphere. And you can see these kind of curve. Notice they're above, below, then above again. So they're not really rising in a straight line. They're curving, which means it's shallower in this region than it is up here. So that means it looks like the carbon dioxide in the atmosphere is increasing at an increasing rate, which is troubling to many people. So let's see, which 2 points? I think 1970 is a good one to pick, and then maybe 2000. So let's isolate those two. 1970 and 2000 are the points we're going to pick on. Highlight them, and then we'll play around trying to find a slope. So first, let's type some stuff up here. So I need a rise and a run for those two. Let's go over here. So rise is going to be this second number minus the first one. Pull it up again. And the run is going to be the change in dates, which we can see pretty plainly. Oops, forgot to type equals. It's going to be 30 years, but what the hell? Let's have a spreadsheet double check for us. And interesting way it formatted that. Center those to make it prettier. And then we want to find the slope. And so the slope is equal to the rise divided by the run. So my spreadsheet says the slope's around 4.5, or let's see, we have those numbers to 5 significant figures in terms of the CO2. The year's kind of not that important. It isn't, so let's drop this down to, is that 5 right there? Right there's 5 significant figures. So 1.4573 would be the increase in parts per million per year, because we took parts per million change divided by change in year. So let's write that up in our spreadsheet. So I need a screenshot of that. All right, so I want to see the data and the slope. All right, there you are. All right, so again, just a reminder about what I did here. I wanted to find the slope. Let's switch colors, and the slope is always the change in your output divided by change in input. And this is my output here, and this is my input there, right? So that's like our X and my Y. And so we took 369.4 minus 325.68 divided by the change in year. And the order of the numerator doesn't matter too much, but you get to get the denominator right. So since 369.4 is right there, the year 2000 has to go under that because they're the same point. And 325.68 has to go with 1970. And so that gave me 43.72 over 30, and then that to 5 significant figures was 1.4573. And again, this is parts per million, so let's label that parts per million versus years. So this change would be an increase because it's positive of parts per million per year of CO2 in the atmosphere. So we have the slope down. Next, to find the y-intercept, we would plug that into y equals mx plus b. So, and we could plug either the point for 2000 or the point for 1970 in. Doesn't really matter which one you do, you get the same result either way. So I'm going to go for 2000. So in 2000, y was 369.4, and that should equal the slope 1.4573 times x, which is 2000, plus b. And so now we can solve for b after we plug that in. So I'm going to go back to my spreadsheet, and I'm going to double check it both ways using the first point and the second point. So spreadsheet is a calculator, right? So I'm trying to estimate b. And if you look back again at what I wrote here, I'm going to have to do that multiplication, then I'll subtract it over to the left. So summarizing that here, I want the y value here, subtracting the slope 1.4573 times the year. And in that case, I get a negative 2,545. Well, that's a crazy number for the B parts per million. Let's see if I got that right by using the other point. So let's check. So the other way, I'm just going to plug in these two. So that number minus 1.4573 times the year. And I should find I get about that same crazy number. Damn. Okay. So that's a crazy looking number. So how do we deal with that? Well, remember what the y-intercept is. The y-intercept goes when you hit the y-axis. That means I'm looking at the point 0, whatever b is. All right, so let's see. B, well, that's parts per million. 0 is the year. Year 0. Let's think, what does year 0 mean? Uh-oh, that was like 2,000 years ago. So that's not really related to my data set here. I only have data back to 1960. So usually, talking about year 0, right, the change between AD and BC, that's a little weird in most contexts. Doesn't work too well. So the way we compensate for that is instead of looking at the actual year, we pick a starting year that's closer to us. So I'm going to insert a column here. And sometimes we might do things like the years after 1960 or the years after 1900. I'm just going to go with 1960 because that's the first one I have. So I'm going to make a new variable. I could call it t, and t is going to be the number of years after 1960. And let's word wrap that so we can see it, or just make that wider, I guess. So that means this would be year 0, and this would be year 5, and I think we're going in 5-year increments pretty steadily here, so then I can just fill that pattern down. So 2010 would be 50 years after 1960. So it turns out that's going to make the y-intercept easier, because if this is my 0, then that is my y-intercept right there. Right? So that takes out the weirdness of looking at year 0 being 2,000 years ago, and we get something that's more related to our data. So my b in this case is just going to be equal to 1960's value. Okay. Some people say, well, starting in 1960 seems kind of arbitrary. Why don't you start in the year 1900? Okay, I could do that too. So if somebody didn't like that idea, we could just change it. So let's change it. It makes the math a little more interesting. Not quite as easy, but it's all right. Oh, not 2000, but 1900. Try again. All right, so that means this would be year 60, and this would be year 65, and so on. And so I can just fill and overwrite those numbers. So that'd be 110 years later. So now I have a little work to do to find b again. But it's not too different than before. I'm going to use 60 years later and that value. So then I think my b is going to be equal to the 1960 value minus the slope, 1.4573, times the x value, or the t value here, which is 60 now. And so now I get a y value of 229.47. Now that would be, what does that mean? Well, year 0 here would be the year 1900, so we could say that is a prediction of the CO2 in the atmosphere, parts per million in the year 1900. And I don't have that data right now to confirm, but I doubt it's accurate, because that's a little outside of my data here. But I think I have a model now once I rewrite my variables. So let's define some variables, which I kind of skipped. So now we're going to say that x is the number of years after 1900. So that means 1970, for example, would be year 70. And 2000 would be the year 100. And 100 minus 70 is still 30. That doesn't change anything about my slope. I'm just kind of sliding my line left and right a little bit to figure that out. Then y, that hasn't changed. That's just the average parts per million. Average parts per million CO2 in our atmosphere. And since I've rewritten that, instead of plugging in, say, 2000 here, I would plug in 100 to get B. So I forgot what that was. It was 220 something, wasn't it? 229.47. So I think the y-intercept now, B, is 229.47. And you might be saying, whoa, wait a minute. You plugged in the year 1970, not the year 2000 to get that. This is true, but it shouldn't matter which point you pick. So let's just double check on the spreadsheet. So here again, I found that B by plugging in, actually I plugged in 1960. Oh, that's going to change things a little bit because it's not one of my starting points. So I should have picked 1970, which would be, what, C4? 223.67. Oh, that did change a little bit. Okay, because again, it wasn't one of the 2 points I picked for the slope, is why it's changing a little. So 223.67. And I highly recommend crossing stuff out instead of erasing it, just in case you decide, oh, that was better. 223.67. Yep. All right, so let's check it for the other yellow point. It should match for that. So I'm going to recalculate B, hope it's the same. So in that case, I want my y value minus the slope, 1.4573 times the number of years since 1900, which would be 100. And yes, I could have clicked on it there. And I get 223.67, the same one. So now I have a linear model for this situation, given my redefinition for what the independent variable was. So back here, let's just grab that into a new screen, make it a little cleaner. All right, so again, we have X is the number of years after 1900. And Y is parts per million CO2 in atmosphere. Then the equation I get based on those variables and those 2 points is y equals 1.4573 times x plus 223.67. Did I remember that right? Yep. So that's my linear model. Shall we check the linear model? Of course we should. So to check it, I'm just going to run it through all of these years to see if I get numbers that are similar over there. And again, the spreadsheet makes that happen so darn fast. So I'm going to model those numbers. And let's highlight that in a different color. Where's my colors? There it is. And CO2 in the atmosphere is kind of gray. So we think that the model looks like this. Slope 1.4573 times the years after 1900 plus 223.67. And what we should find that sometimes it's pretty close, especially for those 2 yellow points I picked. And otherwise it's going to be not exactly, but close. So let's see. In the beginning, I have an underestimate, and then I pretty much nail it at the years I picked with a little rounding error because I rounded the slope. And then otherwise, I have an overestimate over here in the middle, back to nailing it. And then over here, we have another overestimate, right? Or is that an underestimate over there? And if you look back at the graph, what we're trying to do, we were trying to put a line through there. So my line is under for the first couple points, nailed. I designed it to nail that point, and I designed it to nail that point. Otherwise, the line is an overestimate in between, and the line underestimates the actual points later. So do I have a model that approximates the amount of CO2 in the atmosphere in the years 1960 through 2010? The answer is yes, I do. Does it nail it exactly? Well, no. But again, this is average CO2 across the whole planet, which varies from place to place. It's not uniform, but we'll call it close enough. So again, the trick here was I had to redefine the independent variable. Instead of calling it the year, I did years after some starting point. And starting points can be something like the first year in your data, or they could be some convenient year like 1900 or 2000. And it just kind of depends on what you're doing. Your job in the next couple of assignments, you'll have a minimum wage to estimate. And the minimum wage numbers line up pretty nice. That's one of your problems. And the other problems are related to height of adult males between the ages of like 2 and 15. That's relatively straight line. And then let's see, what's that other problem you're going to look at? Tuition, I think, is that last problem. Let's double check. Your last problem to look at this week. You have 3 major problems to analyze. For the rest of the week. Share your work. Yes, tuition and fees at public four-year colleges. So these, you can see they got a little bit of a curve to them, but we're going to put our best straight line through there. So you're going to have to decide which 2 points you want to pick to make your straight line through there. And here I recommend using T being years after 2000 to make that easier. And I provide a spreadsheet of that if you want to do some similar things to what I did in this video. All right, well, do good math, stay in touch, and I'll catch you in the near future.